several different temperature readings we're taking. The thermocouple is a fairly fickle and sensitive device, so it can change quite rapidly. And so in order to find an accurate temperature, we needed to take several readings and then average them all. In order to come up with a value for the, or rather an algorithm to calculate the temperature, final temperature, we had to conduct a study of thermocouples. Mostly suggested that you use either a quadratic or a cubic function. Although through our research and our taking of data, we discovered that the actual values for at least our range are fairly linear according to the voltage and according to the thermistor temperature. As a result, we came up with a value that was linear according to both of these. Although originally we were considering using a complete chart of values, just a lookup table, it was found that the required memory would far exceed any sort of doable situation on our part. So we decided to kind of sacrifice a little bit of the accuracy, go with a linear equation so that the power would still remain low, which is one of the main purposes of using the GS1010. And with that, I'll hand things over to Andrew to discuss how this came together as a whole.
So this is our main schematic. I know it's kind of hard to see, but when we put everything together, we wanted to make a PCB because one of the requirements is supposed to be on an object. It's going to be tracked, so it has to be small. So obviously we can't use this big development board that we got. So what I did was I took a bunch of the schematics that Gainspan was nice enough to provide me as reference, which was great because it helped me understand there's about over 100 pins on the actual GS1010. So, and there's about maybe a dozen different powers. So the schematics they gave me helped understand where everything was wired to, and it was especially helpful figuring out where the bypass capacitors needed to be. But as you can see, some of the schematics, or some of the parts of the circuit that we talked about already. Up here is the motion detecting part. This is the accelerometer going into the analog multiplexer. And in the lower right here is the temperature sensing area. This is the circuit that Dave talked about that biases the thermocouple reading so that we get a positive voltage no matter what. And then it's amplified by the op amp. And then that input goes into one of the ECE pins. And the thermistor that he was talking about earlier goes into another one of the analog multiplexer pins. The analog multiplexer, the output from that is selected from just a general purpose output pins from the GS1010. And there's actually two different clocks for the GS1010, one for the low power state and one for when it's fully active. So the fully active one runs at 44 megahertz, while the low power one is actually only 32 kilohertz. So after discussing, this is about the fourth revision of this schematic. A couple of my classmates were able to help me pick out a few of the major bugs in the first version of the schematic, and then I sent it off to Gainspan twice, and their systems architect helped me narrow down all of the mistakes, especially having to do with bypass capacitors. That was a little finicky. And we ended up getting this out to production. This is our final PCB. As you can see, I put a nickel in here for scale, so it's pretty small. We have our thermocouple connected right here, powered by 2 lithium-ion batteries. And unfortunately, we didn't populate the rest of the board because we had a problem with Gainspan actually getting us the parts. We've been waiting now for a couple of months. So, it's going to be programmed over UART. This is a 6-pin UART connector, and if you come down into the lab at 12, you can see we have a 6-pin UART to USB cable that we'll use to program it using the programs that they provided us to load code onto it. And in the future, they wish to have it once the initial program has been loaded onto it, be reconfigured over wireless, although we haven't encountered that yet either. But so this is where we are right now.
Yes.
Any questions?
Two questions about the motion detection. First, how do you handle vibration? And second, how do you handle the gravity?
What do you track the gravity?
Well, you're going to get an accelerator. One of the pins is going to bend due to gravity, right?
Okay. Well, the gravity part's kind of easy. Part of the way that it detects the actual algorithm for detecting motion samples 500 times, so it doesn't really matter which orientation it's in, as long as the deviation between recorded samples doesn't move too much. So as far as vibration, we haven't really tackled that yet, because their motion detection isn't really a really big priority for them. They kind of want to know what's on or off. Previously, they had been using just a metal ball in a glass tube kind of a thing, like if it hits one of the ends. So we have in code that you can program its sensitivity. So if you know that it's going to be in a situation where it's going to be vibrating a lot, you can make the sensitivity larger. And if it's going to be in a position where it's pretty much just sitting like on this desk and it's not going to go anywhere, then you can really narrow down that sensitivity so that anything will set it off.
Yeah, did you come up with a cost?
Yes, we did. For the beta cost, this isn't a production cost. If we were just going to make another one, it came out to about $120. But a lot of that cost would go down. A significant portion of that is the PCB manufacturing, and some of the components that would cost about $7 to $10. Their price would be cut in half, and all the smaller components that add up, like capacitors and conductors, would obviously go down as well. I think the biggest cost is actually the GS1010. It costs $25 for one.
Just wanted to add, because I've been involved with this project, that the number of applications on a pragmatic basis is very high. For instance, in the hospital for tracking, it can be infusion pumps and so forth, but also within the cold chain within a hospital, such as transporting blood, bone marrow, tissue, things of that sort. Monitoring the temperature as well as the location is a critical component. And then on a different scale, but in your food industry, again, the cold chain operations with this temperature sensing as well as location is quite a lot of commercial potential.
Other questions?
A 3-year battery life is a long time. Can you explain the major power draws and how you assume what state the system is in for that 3-year period?
I don't have the actual calculation from you, but so when the device has the operating system has a dynamic power saving routine, so it shuts itself off into a very, very low power consumption when it doesn't have any tasks to run. And we don't have a very high overhead task, so most of the time it's going to be in sleep. The most power consumption or consuming states are when they're in wireless transmit and wireless receive, which they can only afford to do that a fraction of a second every couple minutes. Because right now we've been testing on it sending once every 15 seconds, but that's just for our testing. We haven't actually gotten a good power test, but the people that we've been talking to say that it's pretty reasonable to expect under a second transmit receive.
So did you try any typical applications, like in a hospital, something like a piece of equipment that moves twice a day from one room to another, and run that through for 3 years?
No, we haven't. Like I said, we haven't had